this is section 10.1, which is on Laplace transform. So let's first define what a Laplace transform is. So suppose f is a function of t, and it's defined for all positive values of t. Then its Laplace transform we have two notations. We either use capital F of s or curly L of f of t. This is defined to be the integral from 0 to infinity of e to the negative st times f of t dt. So first thing to notice is that the Laplace transform uses the variable s, whereas the original function has variable t. So the variable is different. And the second thing to notice is that this integral is improper because it's from 0 to infinity. So the Laplace transform is defined only for values of s such that the integral converges. Alright, so let's do an example. So let's consider an easiest function, which is the constant function 1. So the Laplace transform of the constant function 1 is equal to the integral from 0 to infinity of e to the negative st times 1 times. And we know how to integrate this. This is equal to negative 1 over s times e to the negative st from 0 to infinity. But because it's improper, we need the exponent to be negative for it to converge. So we need s to be positive for the integral to converge. And if s is positive, then all we need to plug in is the 0 part. This is equal to 1 over s. So the Laplace transform of the constant function 1 is equal to 1 over s. This is for s positive. Right, so next we want to talk about Laplace transforms of polynomials. But before we do that, we have to first recall or introduce what's called a gamma function. So the gamma function is defined to be the integral from 0 to infinity of e to the negative t times t to the x minus 1 dt. This is defined for x greater than negative 1. The gamma function has very useful properties. So first, if you plug in x equal to 1, then x minus 1 equal to 0. So this is just the integral from 0 to infinity of e to the negative t dt, which we know what to do. This is equal to 1. And the second, this is the most useful property, is gamma of x plus 1 is equal to x times gamma of x. You can verify this using integration by parts. Well, with these two properties, we can calculate gamma values of integers. So for example, if we want to calculate gamma of 4, then if we use the second property, this is equal to 3 times gamma of 3. And if we use it again, this is equal to 3 times 2 times gamma of 2. And we do again, this is equal to 3 times 2 times 1 times gamma of 1. But we know gamma of 1 is equal to 1, so this goes away. So this is equal to 3 factorial. And this holds in general. So gamma of n is equal to n minus 1 factorial if n is an integer. Alright, so now we know this, we can calculate the Laplace transform of polynomials. So let's do that. Okay, so let's let f of t equals to a polynomial t to the alpha. Alpha is greater than -1. Then the Laplace transform of t to the alpha is equal to the integral from 0 to infinity of e to the -st times t to the alpha dt. And here we're going to do a u substitution here. So we're going to let u equal to st. And to maintain a bound from 0 to infinity, we need to assume s is positive. Alright, so if u is st, then du is s times dt, and t is equal to u over s. So we can plug all these in. The bound is still 0 to infinity. This is equal to e to the -u times u over s whole thing to the power alpha, and dt is du over s. So arranging terms, this is equal to the integral from 0 to infinity e to the -u times u to the alpha times u to the alpha times 1 over s to the alpha plus 1 du. We can take this whole thing out. So this is equal to 1 over s to the alpha plus 1 times the integral of the remaining terms. But notice that this is precisely equal to gamma of alpha plus 1 by the definition. So the Laplace transform of t to the alpha is equal to 1 over s to the alpha plus 1 times gamma of alpha plus 1. In particular, if alpha is an integer, then the Laplace transform of t to the alpha is equal to 1 over s to the alpha plus 1 times alpha factorial. So for example, Laplace transform of t squared is equal to 1 over s cubed times 2 factorial, which is 2. Laplace transform of t to the fourth is equal to 1 over s to the fifth times 4 factorial, which is 24 over s to the fifth. All right.